Hello guys, welcome to my podcast. I'm your host Rupesh Gaikwad. Today we will discuss about shell balance for momentum transfer, which is a fundamental topic in transport phenomena. To know more about the topic, I have invited my fellow batchmate Nalin. Welcome Nalin.
Hi Rupesh, thanks for inviting me to your podcast. It would be really great to discuss on shell balance for momentum transfer, which is a very fundamental topic in transport phenomena, as you said. And I'm really, honored to discuss this with a genius mind like yours.
Thank you.
And I think it would be unfair if we directly jump to the questions. First, we can discuss a bit about transport phenomena and then a bit about shell balance, and then we can further solve the questions.
Right, it will be a great approach for the podcast. So, what do you know about the transport phenomena?
See, transport phenomena is a very wide and very recognized subject in chemical engineering. If you aspire to become a very good chemical engineer, you really need to grasp the fundamentals of transport phenomena. For better understanding, have you ever heard about 3-in-1 ice cream?
Yes.
So see, transport phenomena is very similar to a 3-in-1 ice cream. Transport phenomena is combination of mass transfer, heat transfer and fluid dynamics. If you have ever thought about a fluid flowing through a pipeline or a heat flowing through a reactor, it all is basically transport phenomena. It is the science behind the scenes through which you can relate the theory to the real world engineering problems.
Okay, so it's a combination of mass transfer, momentum transfer, and fluid mechanics all in one.
Exactly, yeah.
Right.
It's all in one, and if you really aspire to become a very good chemical engineer, without transport phenomena, I'm sorry, but you can't do it.
Okay, so it's a very important subject for becoming a good chemical engineer.
Exactly.
Right. So that was a very good brief about transport phenomena.
Thank you.
So we'll discuss about the shell balance for momentum transfer.
Yeah. What are your views on shell balance?
Right. What I know about is it is a shell balance technique for calculating or deriving the velocity profile. Basically, it's like you imagine a shell or a differential volume, and then you discuss about the dimension and discuss about the momentum entering, leaving, and generating inside the shell.
So basically, you are saying that we take a differential shell and we apply force balance on it.
Right. Force balance, entering force, leaving force, and the generation
Basically,
of energy.
We can take a coordinate system depending on the problem, like it can be a Cartesian coordinate system or a cylindrical or a spherical coordinate system, which we can understand through the problem.
Yes.
And then we can further apply force balance.
Force balance.
And to get the basically velocity profile or temperature profile or so on. Like here we are focusing on momentum transfer. So basically we will get velocity profile and flux profile.
Flux profile as well, right. So let's discuss about a few problems. Like I have a question about it deals with parallel plates, flow inside a parallel plates.
Okay.
So I'll give you a problem statement about it, and we'll discuss about the problem statement and derive the velocity profile.
Sure.
Right. So Nalin, here's a problem of fluid flowing between the parallel plates. The problem says that the no slip boundary conditions is typically applied, but in practical it is not the case, right? So if the slip should occur, then Jackson he suggested that the following boundary condition can be applied. That is, velocity of the fluid near the wall or attached to the wall is equal to velocity of the wall, constant velocity of the wall, plus beta times derivative of the velocity of the fluid. So we have to apply this boundary condition to the upper wall, which is moving with velocity v wall, and in the presence of pressure gradient, we have to obtain the velocity profile between the walls. So how we can approach?
So see, the most basic thing is that in this question you can first use the basic shell balance, and you will get to a point where generally we apply that no slip condition.
Right.
Then for this question you cannot do that because it's specifically mentioned there. There you will use this velocity equation which is given, and then you can further integrate this and use the boundary conditions like we generally do in our problems, and therefore after applying the boundary conditions you can get your velocity profile as expected by the question.
Okay, so you mean to say that we have to approach with the basic
Yeah.
procedure?
Firstly, you have to go with the basic procedure of shell balance,
Right.
and then at that point where we generally use our no slip
No slip
condition, then
condition.
you can go with this equation and then further integrate it. Using boundary conditions, you can get your velocity profile depending on the question.
Okay, so now we'll approach to solve the question.
Yeah.
So as we have discussed the problem, now we will jump on to the solution. First we will like to draw the diagram of the problem. Since it is a fluid between two plates, the dimension of the plate will be L, which is the length of the plate, W, which is the width of the plate, and distance between the two plates is 2b. As discussed in the problem, the upper plate is moving with velocity vw, which is constant. The coordinate system we will choose here will be Cartesian coordinate because it is understandable. The origin will be the middle section of the plate. If we draw the diffraction shell, it will look like this is the length L, this is W, and this is delta X because it is differential shell. This is the origin where the Cartesian coordinate are Z direction, X direction, and Y direction. From the problem, from the shell or from the problem, we can see that velocity in Y direction is 0 because the properties do not change in that direction. The velocity in X direction is 0 because no fluid flows in vertical direction. But the velocity in Z direction is function of X direction. It is function of X because since the upper plate is moving with velocity Vw, the molecules under it will also move with that velocity, which is a function of X. So we have only one term, Vz equal to Vx. Pressure is a function of Z. Now we will look into the forces flux into area. Actually this is rate, in and out. Here the non-vanishing points are associated with velocity Vz. So it is rho xz into pressure plus rho Vx Vz plus tau xz. This is equal to 0 because tau I is not equal to j, hence it is 0. This is 0 because Vx is 0, but this is not 0 because as we know that if we expand this term, it will look like dou Vx upon dou z plus dou Vz upon dou x. This is 0 because Vz is 0, but this is not 0 because as discussed earlier, Vz is function of Vx. Hence, xz is
minus nu dou v divided by x, which is equal to tau xl. Say this is equation number 1 is equal to pressure plus rho Vy Vz plus tau Yz. It is 0 because I is not equal to j. It is 0 because Vy is equal to 0, and this is 0 because Vy is 0 and Vz is not a function of Vy. So phi Yz is 0. Phi Zz, rho Zz into P plus rho Vz plus tau Zz. This is P and rho Zz delta Zz is equal to 1 because I is equal to j. This is 0 because Vz at surface at x equal to x and x equal to delta x is Vz is 0. This is 0 because Vz is not a function of z, hence phi Zz is P. Now we will balance the rate in and out. Phi xz at z equal to 0. Actually this is x. Phi xz at x equal to 0 multiplied by area will give us a rate. Area perpendicular to phi xz is LW, and phi xz at x equal x plus delta x is out. Phi zz at z equal to minus L by 2 into the area delta x into W, and out is phi zz at z equal to positive L by 2 into area z into W. How this, if you look into the differential shell, it is like a cuboid, and we have chosen origin in the middle part of the shell. Since this is the middle part, distance from here is, this is L distance. Distance from here will be minus L by 2 and this will be L by 2. This is the middle part. Distance from here and here will be half of the width, and this is the middle part, and distance from here will be half of 2b. So this is b and b, and this will be delta x. Now we will look into the balance equation, that is in minus out plus generation minus consumption equal to accumulation. This is 0 because there is no generation, this is 0 because there is no consumption, and this is 0 because steady state. So the balance equation is in minus out equal to 0. Now we will substitute the rate. LW phi xz at x equal to 0 minus phi xz at x plus delta x plus delta x into W phi zz at z equal to minus L by 2 minus phi zz at z equal to positive L by 2, which is equal to 0. This is in, this is out, this is in, this is out. Now we will rearrange the equation. So rearranging, we get phi xz at x equal to 0 minus phi xz at x plus delta z upon delta x, which is equal to phi zz at z equal to positive L by 2 minus pi z z at z equal to minus L by 2 upon L. The minus sign is also accomplished in the rearranging. Applying partial differential equation formula. For this bracket, we get dou phi of xz upon dou x, which is equal to p L minus P naught upon L. Phi xz is tau xz, and this is minus delta P upon L. Here it is minus, and this minus will accomplish this, so we can cancel out, because delta P is equal to P naught minus PL upon L. Now, since we have get one equation, that is dou of tau xz upon x is equal to delta P by L, we will integrate to get flux profile equation. Tau xz will be delta P upon L into x plus C1. Now it is given in the question that there is a slipping of molecules. So we will look into the equation given in the question. It is given that velocity at the wall is of fluid at a wall is v wall plus beta dou of v on dou x at wall. This is velocity of fluid, and this is velocity of wall moving with constant velocity. Now, boundary conditions. Before applying boundary conditions, we will substitute, or we will apply Newton's law of cooling. That is tau xz will be equal to minus nu d of vz upon dx, which is equal to delta p x upon L plus c1. To get velocity profile equation, we have to integrate and rearrange this equation. So dvz upon dx will be minus delta p upon L into nu into x minus c1 upon nu. Integrating, we get velocity as delta p minus delta p L nu x square upon 2 minus c1 by nu into x plus c2. Now we need boundary conditions to get the value of constant c1 and c2. So the boundary conditions are: at x equal to minus b, velocity vz becomes 0, and at x equal to positive b, velocity is given as v wall plus beta d of v upon dx. Applying the boundary conditions, we get for x equal to minus b, velocity becomes 0. So 0 will be equal to minus delta p upon mu l into b square upon 2 plus c1 into b upon mu plus c2. So we get c2 equal to delta p upon mu l b square by 2 minus c1 by mu into b. Say this is equation 1. For boundary condition second, delta x at equal to p, vz is given as v wall plus beta dou of v upon dou x. v wall plus beta dou v upon dou x will be equal to minus delta p upon mu l into b square by 2 minus c1 upon mu into b plus c2. We have calculated the value of c2, which is this. We will put or substitute in it. We get delta p upon mu l b square by 2 minus c1 upon b. This term and this term cancels out. We have minus 2c1b upon mu. Say this is equation number 2. Now we know another boundary conditions, that it at x equal to kb, this is kappa, we get v equal to v max and tau equal to 0. Say at distance kb we get velocity at maximum condition and tau becomes 0. So from the equation of flux, which is C1 will be equal to tau xz equal to 0. So delta p upon kb upon l. C1 equal to minus delta p kb upon l. After substituting values of constant, the velocity equation becomes rearranging the equation, we get integrating the equation. Now to get the value of constant C3, we also need another boundary condition, but we will choose the boundary condition taken earlier, that is at x equal to minus b, velocity becomes 0. So the value of constant comes out to be to be 2 delta p k b3 b to the power 3 upon beta nu l minus velocity of wall into beta upon b. So the overall the velocity equation becomes at slipping condition, velocity is equal to 2 delta p k into b square upon beta nu l into x minus velocity of wall upon beta into x plus 2 delta p k beta to the power 3 upon mu l b beta minus velocity of wall into b upon beta. Rearranging, we get velocity equal to x plus b to the into 2 delta p k b square upon nu l beta minus b wall upon beta. You can see that if we apply the boundary condition, say at x equal to minus b, the velocity must be 0, and this satisfies it. The equation satisfies the boundary conditions. Hence, this is the required velocity profile equation for the given problem. We will summarize the problem. This is a problem of co-ed flow, which is the fluid flowing between two parallel plates. This is the diagram of the problem. The dimensions of the problem are L, W and 2B. The coordinate system selected is Cartesian coordinate and the origin was taken in the middle section of the diagram. The differential shell becomes delta x, distance between the two plates, W and L. From the shell we can see that velocity at y is equal to 0 because properties do not change. At velocity of x direction is 0 because no fluid flow in the vertical direction. Velocity is a function of x for the velocity of z direction because the velocity of ball which is moving with constant velocity drags the molecules beneath it. Pressure is a function of z direction. The non-vanishing points are associated with Vz. Phi xz becomes equal to tau xz and phi yz is 0. Phi xzz is equal to p. If we balance the rate, substituting the in and out, we get the balancing equation as tau xz is equal to delta p into x plus c1. To remove this constant c1, we have used the conditions given in the question. It was given that slipping occurs with the given velocity as v ball plus beta into dou v by dou x. The another boundary condition which we used in the problem are at x equal to minus b, vz is 0 and at x equal to b, vz is given condition for the slipping ball. At x equal to minus b, if we substitute vz equal to 0, we get the equation for c2. And at x equal to b, if we substitute the given condition for the slipping, the velocity equation becomes equal to this, equation number 2. We have to apply another boundary condition. Let's say at distance kb, the velocity becomes maximum and tau xz becomes 0. Using this condition, we got to know the equation of c1. After substituting c1 in the velocity equation and integrating the velocity equation, we get another constant c3. To remove this constant c3, we have applied the boundary condition 1, which is at x equal to minus b, vz is 0. So c3, the value of c3 is this. Substituting it in the velocity condition and rearranging the equation, we get the velocity profile. This is the final velocity profile of the problem. Thank you.